everyone and welcome to this video. Today we will continue talking about reversible reactions, and our topic today will be the equilibria in gas reactions, the equilibrium constant Kp. Let's start. Now we talked before about the equilibrium constant for liquids and we name it Kc, and we assumed that for solids it will be equal to 0. But what about if my reactants are gases? If my reactants are gases, it is hard to calculate or to measure the concentration. Instead, we will use what we call the partial pressure. Now, the pressure of my gas usually is equal to the pressure or the bombarding of my gas molecules to the walls of my container. My partial pressure would be the pressure of this gas exerted on that container at the same volume when it occupies this volume by itself. Let's understand the partial pressure more. And now if I have this gas A that occupies this certain volume and I have this gas B, I will consider this to be my partial pressure for A, and we will name it partial pressure A, and I will name the second one to be partial pressure B. Now, the total partial pressure would be the sum of those two partial pressure of my gas A and my gas B, and this I will assume it to be partial pressure T for total. So now, if I have this partial pressure for my gas A is, for example, equal to 8 Pascal. Now, if my partial pressure for gas B is equal to 3 Pascal, this means my total pressure would be equal to 11. Now, if I need to express the equilibrium expression for the partial pressure, in that case, it will be similar to Kc. If you remember, the Kc we said before is equal to the concentration of my product divided by the concentration of my reactants to the power of the number of moles. P would be similar to that case, and in that case, if I assumed I have this reaction where I have nitrogen reacting with hydrogen to give me ammonia, my Kp product divided by the partial pressure of my reactants, and you could see here to the power of the number of moles, and here of course it is 1. Now let's look at this exercise. In here I have nitrogen reacting with oxygen to give me nitrogen oxide. I need to know the partial pressure of nitrogen oxide. If I know that the total partial pressure is equal to, P total is equal to 10 multiplied by 10 to the power 4 Pascal, and the partial pressure of nitrogen and oxygen, both of them is equal to 4.85 multiplied by 10 to the power 4 Pascal. Now if I need, I know that the partial pressure of my reactants plus my products is my total partial pressure. So if I know that Pt is equal to P N2 plus P O2 plus P NO, now I know that both of them is equal to 4.85 multiplied by 10 to the power 4 Pascal, and I know that this one is 10 multiplied by 10 to the power 4 Pascal. Now I can find out the partial pressure of nitrogen oxide, and it will be equal to 10 minus 4.85 multiplied by 10 to the power 4, which is equal to 5.15 multiplied by 10 to the power 4 Pascal. Now, in industry, sometimes we have reversible reactions, and our rule is to find out the best condition to have the highest yield. In here, you could see in production of ammonia, I have nitrogen gas reacting with hydrogen gas to produce ammonia. In here, I have 4 number of moles, and in that side, I have only 2 moles. So if I increase the pressure, my reaction would be forced towards the less number of moles. So increasing the pressure in that case would push my reaction to produce more ammonia. It is an exothermic reaction. This is why reducing the temperature would increase the rate of my reaction, because it will just produce more ammonia where there is an exothermic reaction is happening. Now I also, if I remove the ammonia as soon as it is formed, my reaction would start to compensate the absence of ammonia by producing more ammonia. So my best condition would be lowering the temperature, increasing the pressure, and in that case also removing the ammonia by condensation once it is formed. Now, if I looked at the reaction of production of sulfuric acid, it is also an exothermic reaction. And if I increase the pressure, because here I have 3 moles on that side, and here I have only 2 moles. So if I increase the pressure, in that case, I would have more product towards the least number of moles, which is the forward direction. And also, if I decrease the temperature, I would produce more SO3 in my reaction. Now you have to remember one thing: increasing the pressure in this reaction is a little bit dangerous. This is why we rely on decreasing the temperature, because it is an exothermic reaction, and we don't play much with the pressure because we almost do it at room pressure, because it is very dangerous to increase the pressure of my reaction. Now let's look at this exercise. In here I have the Haber process to form ammonia in industry, and you could see it's an exothermic reaction like we said before. And then here I have 4 moles, and here I have 2 moles. So usually why we don't increase the temperature more than 450, this is because my reaction is an exothermic reaction. So I need more ammonia, so I need my direction to be pushed to the forward direction or to the right. This is why I don't increase the temperature. And why I carry out this reaction at a high pressure? This is because if I increase the pressure, my reaction would be directed towards the fewer number of moles, and this would be my forward direction. So my reaction would be shifted towards the right if I increase the pressure. Why we remove ammonia as soon as it is formed? This is because if I remove the ammonia, my reaction would try to compensate the missing ammonia by producing more ammonia. So my last point is why when we remove the ammonia, it doesn't decompose back to nitrogen and hydrogen. This is because ammonia have a high boiling point. This is why it doesn't decompose back at a normal temperature. For ammonia to decompose, we need to increase the temperature. This is why at normal temperature, ammonia does not decompose into hydrogen and nitrogen. By that, we came to the end of this video. Next video, we will talk about acid-base equilibria. Until next video, thank you and goodbye.